Let's look at the example of how we find the Fourier coefficients and also the DC components. And in this one here, we have ft is a pulse that goes from 0 to 10. And for this waveform, it is quite clear the fundamental period t is 1 second. So therefore, omega is equal to 2 pi over t. That's equal to 2 pi. And the A0 is just 1 over t from 0 to t. In this one, we're not gonna go from negative 0.1 to 0.9. Ft dt. And now we can integrate in two intervals, right? So one interval here, t is equal to 1. And we go from negative 0.1 to 0.4. And during that interval, we have a t and dt plus 0. And 1 over 1 goes from 0.4 to 0.9. We have a 0 dt. So this term is going to be 0 for sure. And again, the first term, we have a 10. So we have a 10 times 0.4 minus negative 0.1 plus 0.1, we have equal 5. So this is the average, which is very clear. That's the area underneath this curve, right? So the base is 0.5, the height is 10. This should be 5. And let's look at the AN. The AN is going to be equal to 1 over t and 2 over t. Goes from 0 to t. And ft, and then here we're not going to go from 0, so we go from negative 0.1 to 0.9. Instead of 0.9, I'm going to directly go 0.4 because the other half period, this ft equal to 0. So ft, and I can directly write here is 10 times cosine n omega t, and omega is 2 pi, right? 2 pi t dt. And if I integrate this, and they integrate this one here is, I got a 1 over, I got to replace t by 1, so I got a 2. Also, I multiply this 10 out, and then I have also based on the fact that cosine, let's see, the ax, so we have d sine x sine ax dt, d sine at dt is going to be equal a times cosine at, right? And therefore we have cosine a dt, so therefore we have cosine at dt is equal 1 over d sine at. And therefore we have 1 over, so the 1 over a is going to be n times 2 pi, right, times d sine 2n times 2 pi t, right? So therefore the AN is going to be equal to, by the way, we're going to evaluate here and from 1 to 0.4. I have, that's going to be 20 times 1 over n times 2 pi. And don't forget about dt. No, that's it. And we're going to evaluate that the sine n times 2 pi t. And evaluate that t equal to negative 0.1 and 0.4. And if you evaluate this one here, you get we got a 10 over n pi, right? So we have sine, if we replace t by 0.4, that's 0.8. That's 0.8 n pi. And minus negative, so a minus plus, so we replace this by plus sine 0.2 n pi, right? And we also know the trig identity. And this is not really necessary, but it will give us a little bit of better insight into this Fourier coefficient. And sine x plus sine y is going to be equal 2 times sine half x plus y times sine cosine x minus y half x minus y, right? So that's the trig identity. And if we apply this trig identity here at this x, and we're gonna have an is gonna be equal 10 over n pi, and so we have a 2 here, 10 times 2 over n pi, and times sine x plus y, which is 0.8 plus 0.2, that's 1, divided by 2, n pi divided by 2 times the cosine x minus n pi, that's 0.6 n pi divided by 2, that's 0.3 n pi. Right? So this is the these are Fourier coefficients. I'm just replacing the for the cosine term. I'm replacing this n pi by 2 times 10 by 20. So this is the first an, and we can find the similar using the similar method to find a bn. And a bn is going to be equal to 2 over t. We're going to integrate from negative 0.1 to 0.9. And we have f of t, and f of t now is 10. And by the way, the t is equal to 1, so I'm going to replace everything in numbers. And times sine n omega t, n times 2 pi times t dt. Right, and similarly, we can find this one here is based on the fact that cosine sine at dt is equal negative 1 over a times d cosine at. Right, so in this one here we have 20. Right, we have a 20. We get this 10 out, and here, by the way, we can integrate just a 2.4 we need, and then we have a 1 over times negative 1 over a, which is n times 2 pi, right? And then times the we evaluate that the cosine n times 2 pi t, and t equal to negative 0.1 to 0.4, and here we have 20. We have a 10 over. Let's see, cancel this 2 here. We have a negative 10 over n pi times cosine 0.8 n pi minus cosine 0.2 n pi. And now we need to utilize the trig identity. Cosine x minus cosine y is going to be equal to negative sine half x plus y times sine x minus y, right? And if we apply this trig identity here, and we're going to get a b sub n is going to be equal to, I have a negative sign from these, and oh, I have negative 2 times, and then I have negative 10 over n pi. So we just carry everything out, carry everything over, just don't make any mistake. So we have a sine half n pi, because 0.8 plus 0.2 is equal to 1, and times sine x minus y, which is 0.6, and divided by 2, that's 0.3 n pi. And we finally get the solution here is 20 over n pi times sine n pi over 2 times sine 0.3 n pi. And this is for the bn. And if this is correct or not, we have the Python. I want to reconstruct the waveform using these Fourier coefficients and see if this is correct. So what I did here is the simple Python code, a few lines. So I defined the function, the original function ft here, and this is the original ft, and I calculate the I use the result we calculated for the an, right? 20 over n pi times sine and n pi over 2 times the cosine. So this is for the an, and for the bn is 20 over n pi times sine times 20 sine n pi over 2 times sine 0.3 n pi. And I'm going to reconstruct the waveform using, let's see, I choose a certain number of Fourier the harmonics, and then we're gonna see the waveform. So now I'm choosing like 80 times, and if we want to choose a different number, I think we can. Let's try with a smaller number. Let's try with a smaller number. Let's see, we have. Let's try a number that. Let's try maybe just 3 terms. Let's try 3 and see what that will give us. So this is we only have first and second order and the third order, because second order, if you remember, we have n pi over 2, right? Sine n pi over 2. If the n is even number, actually all these Fourier coefficients are going to be 0. So next lecture we're going to see all the symmetries, and we know why they are actually 0. And if you increase the number, and you get more accurate results. And let's see if we want to increase to 300. I'm having a lot of points. So each period I have 2,000 points. Okay, so let's see if we do 300 with the harmonics, and in that one, let's see, we get a much closer match, right? Much closer match of these. So the orange one is a reconstructed waveform, and then matches the original waveform very well, except the points and the discontinuous points. But if you go the higher order numbers, and those points are gonna getting also match well at those points also. Okay, so that's how we calculate the Fourier coefficients. And the next video clip, we're gonna look at the alternative forms of the Fourier series.